Okay, today's lesson we'll be talking about reflections. I thought I would start with a couple illustrations of some real life reflections. This cat, when he's not toiling around with a ball of yarn, is cutely reflecting into a little pool or mirror or something where he's looking at himself. Next we have this young man looking, reflecting in the mirror, thinking about the day's task ahead. But both of these illustrate the idea of what a reflection is you're just seeing the same image just on the other side. You're seeing that same image reflected about a certain area. In this case, to get math on you, the boy has like a vertical. The mirror is acting as a vertical as the mirror is going up and down. He's seeing his reflection. To go backwards, you can see the cat, it's going horizontally, and now it's creating that up and down type image instead of left or right from what we've seen here. There are a few type of reflections we're going to take a look at. We're going to talk about vertical, horizontal, and then ultimately y equals x and y equals negative x. So let's start with the reflection about the y-axis. If I have the following point here, -3, -2 for A, so we go ahead, we plot our point, -3, -2. What you're really looking for is the distance. As you can see, A is on the left side. You want the distance on the right side that's the same distance and perpendicular, because when we talk shortest distance, we talk perpendicular. The vertical, the horizontal line, those would be much easier to manage. A is 1, 2, 3 points from the line. Go 1, 2, 3 points from the line here, and now you have your new A prime, which would be located at 3, -2. So when reflecting about the y-axis, you will see that it is your x value that changes, but the height, the y value, will remain the same. And just to illustrate that point I was talking about, when a point is accurately reflected about a line, you have the same distance, 1, 2, 3. So we have 3 blocks here, 1, 2, 3, same blocks here, and that distance between those 2 points is perpendicular to your reflecting line. Honestly, on a vertical and a horizontal line, you're going to be best just to count the blocks. Let's take a look at our second one, x-axis. We've got this value right here. A is 4, 3. So we can see we are 1, 2, 3 above the x-axis. So we go 1, 2, 3 below. There's our new A prime. A prime now becomes 4, -3. Again, A to A prime, same distance to the reflecting line, same perpendicular distance to that reflecting line on both sides. Here you see that when we do the x-axis, all that's changing is the y value is becoming opposite and the x value is remaining the same. So that is a rule, but that's one I don't think you need to memorize. That's one where counting the blocks will take over. But again, on an x-axis, the x value will not change, the y will become opposite. For the y-axis, you will see that the x value is the one that changes and the y value does not. What happens if you have a horizontal line that is not exactly the x-axis? Well, in this case, you have a horizontal line. This value right here would be y equal to 2. So what if y equal to 2 is your reflecting line? Same type deal here. If A is -3, 4, count the blocks, 2 above, we'll go 2 below, and A prime would be at -3, 0. So again, 2 blocks above, 2 blocks below. You don't have this pattern where the y values are becoming opposite of one another, but what you do have is that the x values remain the same. So again, a horizontal and a vertical line, clearly best case scenarios when reflecting. Now, let's take a look at one of the more challenging cases, y equal to x. So y equal to x does have a slope. It's really like y equals 1x plus 0. It's this line that I've created right here in green, goes through the origin, up 1, right 1, up 1, right 1. Let's suppose I've got the point, the original point, 4, -1. There's my A point right there, and I want to go ahead and plot its mirror image. Now you can see that I've already had that plotted, but how did we get that value? There will be a rule, but there's also going to be a way for us to calculate this point without maybe memorizing the rule. So from A to the line, you want the same distance. So you know it has to be over here somewhere. you can just kind of line up a mirror image. You can reflect it. But where exactly does it go, and how do you know it would be the same distance from the line and that it would be perpendicular? So we can use the following to our advantage. 1. If I go from A to the line, just map out how you get there. So if I go over 1, 2, 3, up 1, 2. So there's a corner. So if I go left 3 and up 2, just do the opposite to get to the reflecting point. So I went left 3, up 2. So instead of going left 3 and up 2, go up 3 and left 2, and there you will find your A prime. So again, to get to the reflecting line, if you go left 3 and up 2, do the flip, because remember, perpendicular is opposite reciprocal. So you're flipping that. So to go left 3 and up 2, now go up 3 and left 2, and that will put you right here at -1 for A prime, comma, 4. And that will put you the exact same distance from the line, the reflecting line, as you had from A and A prime, and we can see that it's perpendicular. The slope between the two is -1. The slope of this line is 1, so they are perpendicular, and they're each that same distance away. Now, based off the results, you might notice a little pattern here that does hold true. So for every y equals x situation, the following is going to occur. You are going to see xy is going to turn into yx. So whatever your original point is, take the y value, it becomes your x value. Take the x value, it becomes your y value. So here's your original, and here's your reflected point for y equal to x. We had 4, -1. We reflected it. It now became -1, 4. That will occur every single time for a y equals x reflection. Your y value becomes your x value. Your x value becomes your y value. Final reflection we'll take a look at, pretty similar here, y equal to -x, but now we're dealing with some different quadrants here. It's flowing through quadrant 2 and quadrant 4. So I have the point here, -3, -2. A similar approach will occur. How do I get back to that reflecting line on a corner, on a nice corner? You can do this a few different ways. I could go through this corner or through this corner. I'll choose this one for now, just to show you. I go up 1, 2, 3 over 2. So if I go up 3 and over 2, the opposite of that, I know the answer has to be here. So instead of going up 3 and over 2 again, I'm going to go over 3 and up 2, and that will put me right where I need at A prime, which would be 2, 3. Let's suppose I didn't go up 3, right 2, and I went up 2, right 3. Up 2, right 3. So instead of going up 2, right 3 again, I would go up 3, right 2, the opposite of that move. And you see how that puts me right where A prime is as well. So either way works. We see that it's perpendicular. This has a slope of -1. This line has a slope of +1. The distance between A and A prime and that reflecting line are the same. Perhaps you notice a pattern here now. When reflecting about y equal to -x, here's what happens. You take your original point, x, y, and what you're going to see is, notice how the y value sort of becomes the x value. The x value sort of becomes the y value, just the opposite. That will occur every single time. So whatever is your original y value, take the opposite of that. That will be your new x value. Whatever is your x value will become, take the opposite of it, will become your y value. So case in point, just for a follow-up example, if I were to take the point 2, 1, so we'll call that B right here, and I want to just apply the rule. This rule tells me that my new reflected point means take the opposite of y and make that my x value. So there's y, make the opposite. Take the opposite of x and make that my y value. That means that when I go to -1, -2, that would be the correct B prime. let the eyeball test help us out here. It appears that B prime is being accurately reflected about B. So there are the reflections you're looking at. Vertical, horizontal, y equal to x, y equal to negative x, with the specific vertical and horizontals being y-axis and x-axis. A final note about matrix notation. You will see it in this section. We will cover it more extensively after we finish these transformations and we do a separate section on matrices. But if you see it on any of the assignments and I say to put it into normal notation, here's what it looks like. If I were to graph this triangle ABC, which I've done, with the following points in our normal notation, 2, 4, 5, 1, negative 1, 1. This is how I would put it in what's called matrix notation, where the first row right here are all of my x values, 2, 5, negative 1. Row 2 is all of the y values that correspond, 2, 4, 5, 1, negative 1, 1, and each column represents a point. So this is how you would take normal notation and put it into matrix notation. To close off this topic, let's convert one. If you see the following matrix in this position right here, and they say go ahead and rotate it or reflect it or whatever the case is throughout the remainder of the sections we'll be doing here, I want you to convert that into our normal notation. So if it looks like this, remember, row 1 are the x values, row 2 are the y values. So to convert this into normal notation, that means A is located at negative 4, comma 3. That means B is at 2, comma 1. C is at 8, comma negative 5. And then D is at 0, comma 2. While you will see some pros and cons to the matrix for notation, for the problems that we'll be doing here in these sections on the worksheet and just our strictly transformations, we will just be using the normal notation. So hopefully this will help you out when you see those problems that do involve the matrix notation on some of the assignments throughout this lesson and the following lessons as well.